afternoon. My name is Yuri Brovman. I'm a data scientist at eBay in the New York office. It's actually just a few blocks down in Chelsea on 19th and 6th, and we're responsible for all the recommendation systems on eBay. We also do ads optimizations and a few other tasks. And today I'll be talking to you about some of the recent work we've done on addressing the the challenges that the eBay data presents and how do we make recommendations at scale. There we go. So to start off with, I wanted to acknowledge the merchandising team. These are some of the people that contributed to the work that I'll be presenting, and of course the work couldn't be done without them. So to begin, what is eBay? eBay is a marketplace where you can buy and sell virtually anything. But we don't actually sell. We're not Amazon. We don't sell things directly. We connect buyers and sellers. And the variety of inventory on eBay can range from things like electronics, like an iPhone, which is a specific product, through things like a random T-shirt that you find in your basement and want to sell. And now, on eBay, some of the items are these regular listings and don't have specific structured data. Whereas if you have a product like an iPhone, you have specific data attributes like brand, color, things like that are easily listed in tables and can be queried very, very easily. But not a lot of items have that, and that's where we're saying that this is a semi-structured marketplace. So what are some of the challenges that we have to deal with this data when we make recommendation systems? So first of all, just pure scale. On any given time on eBay, there's about 1 billion live items. So just to address that is no easy task. To provide meaningful recommendations to all those items in runtime is not trivial. So scale is something that we have to deal with. There's also 150 million active users as well. So the other part is this data quality, or this type of data, as I mentioned, since it's not all of the data we have that is structured. Another part that is difficult is the volatility of the inventory. So some of the items are listed on eBay for 1 week and they never surface again. They don't have any user interaction. So what do we do with that? That they're possibly unique items and we don't have any structured data for them possibly. So that's another challenge that we deal with. We also have the cold start problem, which is very typical of many recommendation systems where newly listed items don't have user interaction with them. So how do we address these issues? So here are a few of the recent algorithms that we've developed to address some of these issues and provide meaningful recommendations at scale. So the first one is a machine learning ranking approach that we used for the similar items algorithm, where we want to recommend the most similar items to the user when he's browsing eBay. And here we used a point-wise machine learning ranking model. And this work was published last year in ACM Rexis. And that's what I'm going to kind of focus on for the majority of the talk. This was kind of a fun work. It was kind of fun to publish an academic paper with a Star Wars Millennium Falcon on the front page. So another algorithm that we developed is using deep learning. So we noticed that when a user lists an item, we might not have behavioral signals for that item, but we'll typically have an image. And so another way to provide similarity, another degree of similarity that we can try to take advantage of is the picture. Now, just matching RGB values is not that great, but recent developments in ConvNets provide very, very nice comparisons. So we looked at a Google Net convolutional neural network and made a representation of the images. And then we did a brute force k-NAND search on GPU and provided the recommendations based on image similarity. So here at the bottom, you can see on the left column, it's the original seed item. The next three columns are the old recommendations, and the last three are the new recommendation. You can see the last three are very similar to the original item. Maybe it's a little small here. So that was a fun project, and that was using an image-based deep learning approach. Now, of course, there's also text-based deep learning approaches, and we're working on that right now to provide complementary recommendations. And this is where a person has bought one item, and we're trying to recommend you perhaps an accessory, perhaps another item to go with it for a complementary purchase. And here we're using a novel deep learning architecture, training on eBay data. We use Theano as the package, and that's a work in progress right now. So for the remainder of the talk, I'm going to focus on this first approach and go into detail of how we did that. So let's dive in. What is the similar items algorithm? So where is it on the site? So we have an item page here. So we have a picture, a title, a price, maybe a few different attributes of the item. And right below, we have these 5 items. And so these are the similar recommendations. This is the placement that I'm talking about. This is a view from the desktop page, but we, of course, have it on mobile and a few other locations on the site. And so the goal here would be to find the most similar items and to maximize conversion. So we're a marketplace, so we want to maximize conversion, right? We want to get the most amount of transactions, and that's a pretty good goal to optimize an algorithm for. In terms of some engineering constraints, we have 1 billion impressions daily that hit this algorithm, and our response time end-to-end has to be about 200 milliseconds. So that puts engineering limitations on what type of models we can use and what kind of data is available and things like that. Okay, so let's talk about the architecture. This slide is pretty busy, but let's step through it one by one. So on the top left, you have the seed item, and that's the item that the user is actually looking at, and that's the input to the algorithm. And then on the top, you have the recommended items. That's the output. So that's essentially kind of the small pathway there. You have an input. It goes into MBE, our merchandising backend system, and we get the recommendations as the output. So how do we actually serve these? How do we generate the recommendations? Well, we use the familiar two-stage paradigm that's very commonly used in search, where we break it up into 2 stages, a recall stage and a ranking stage. We can't rank 1 billion items at runtime, right? So we first get some candidates that have some degree of similarity to this original seed item, and that's where we have the recall sets, and then we rank those. So let's look at these recall sets. So there's if the item, as I mentioned, has this product ID, like an iPhone would, then we can query our search service, our internal search service, and get several listings based on that product ID. So that's under the products recall set. The second one is using Elasticsearch. So we have item titles that most items typically have, and we can do a TF-IDF match between the seed item and all the other items, and we index all the items on eBay in Elasticsearch cluster, and we can do a very fast text comparison between the titles. So the third one is based on co-views. So this is a behavioral model that takes into account items that viewers have seen and aggregates them and then stores those items in the Redis cache. So we aggregate it from Hadoop, and we store it in Redis cache for fast access at runtime. And the last one is the one I mentioned before using the deep learning, is using item image similarity. So we have this model that we utilize the GPU to get the similar images to the original item. And again, we store those items in a Redis cache available at runtime. So now those are all the candidate items that we can surface to the user. So we have maybe a few hundred, 1,000 items that we've subsampled to. And now we pass it on to the ranking stage. And the ranking is a machine learning ranking model, which I'll talk about in a second. And briefly, the flow here now is from the merchandising backend, we get user information like clicks and purchases. We store the data in Hadoop. We use a Spark ETL job to gather the data, and we have a machine learned offline model where we train our model, and we then pass the model parameters to the runtime system where we rank them in real time. And then we finally complete the loop, and we show the top 5 items to the user. Okay. So how do we actually do the machine learned ranking? So one approach that has been done in search is what's called learning to rank for information retrieval, and where you reduce the ranking problem to a classification problem. Where we have the input to the classifier will be pairs. So in the search case, we'd have a query. So for example, here would be MLConf conference and URL, so some URLs there. So that would be the input to the classifier, and then the target variable would be a binary or multi-class relevance label, Y, and that's typically gathered using crowdsourcing methods to evaluate a relevance. And that could be quite costly and time-consuming to actually get that data. So what we did is use behavioral signals for the class label. So we applied this methodology, and we made a pointwise ranking approach to rank recommendations based on the probability of purchase. So we reduced the ranking problem to a binary classification problem and applied it to these to the recommendation systems. So here's an example of an item page. Again, and so we would have, in terms of our input, we would have the seed item and then the candidate recommended items. And then, so that you can have pair 1, pair 2, pair 3, pair 4. And then the class labels, for example, here would be something like clicked, non-clicked, clicked, purchased, something like this. And just to give you a sense of the data size, the positive pairs, we had about 350,000. So just to give you an idea of the size of this classifier. So just kind of briefly mention one or more features. That we do a lot of feature engineering for the variety of different signals that the items can have. So one important one you might imagine is price. You know, a seed item could be $10. Maybe it's a really old part, and then the new version could be $1,000. So that could be a very wide range in price, but we still have to provide a meaningful score for that feature. So what we did is we took modeled the ratio of the reco price, the recommendation price, to the seed price of the past purchase events. And we fit a Cauchy distribution to that to get the long tails of the distribution to make sure that we have some sort of signal even if the ratio is really high. So that's just one example of our features. And this is a feature that we have that compares the seed to the reco. And then we also have features as well that's things like item quality, which just depend on the individual items. So here's an interesting part. How do we actually select the class labels? So we wanted to get a binary classifier so that we can rank the items based on a single probability score. But now the classes can be selected in a number of ways. So here are some examples. We can have a negative class and a positive class be non-clicked and clicked. We can have non-purchased and purchased, clicked non-purchased and purchased, or non-clicked and purchased. So here are those are some of the combinations that we took a look at. Now at the bottom, you can see on the left side, so this is a probability density, so this is a histogram. And on the x-axis, you have price feature score between 0 and 1. So we normalize it between 0 and 1. And what are the two The two graphs there are, the red is clicked and the blue is non-clicked. So those are the two classes. And you can see that they pretty much overlap. And so, if a human can't really tell the difference between those two, the classifier is not going to do too well either. So we looked at the other sampling strategy of getting non-clicked and purchased. And you can see there's a slightly bigger difference between those two. The red's actually kind of closer to the right. And so we wanted to quantify that. And a quantitative way to evaluate the overlap of probability distributions is called the KL divergence. And we use that as a quantitative measure to estimate the class separability of some of our features. And we looked at all of our features, and we pretty much saw that the non-click purchase strategy is the most optimal one in terms of forming a classifier. And this makes sense in terms of intent, right? A non-clicked item is something that the user has no interest in at all. And then a purchased item is ultimate interest. The user is willing to commit money to that. That's ultimate intent. And then clicked is sort of somewhere in between. And so we decided to use the extremes to train our classifier, to train our binary classifier. So here are some of the classification results. So these are some standard ROC curves and percentage recall curves. And we looked at a few different classifiers. So the baseline model I didn't mention, but it's just a weighted sum model with some human judgment that we use to generate the weights. And we looked at here a logistic regression model, some tree-based classifiers, and a gradient boosted tree model. And we can see we have AUC results in order of in the 70s, and some pretty standard metrics like precision recall, log loss, and things like that. So we saw that when we incorporate this classifier model, we get an improvement in classification performance. So we also look at the ranking metrics. So standard ranking metrics in the learning to rank approach is the normalized discounted cumulative gain. And we looked at that metric, NDCG, at a specific rank, like a rank k equals 1 or rank k equals 5. And here, one important detail here is that that measure incorporates the relevance function. And the relevance function here we defined as the non-clicked is 0, clicked is 0, and the purchase is 1. So we essentially said that the purchases are relevant, and everything else is not relevant. And so again, we can see that the ranking measure was improved as we incorporated our classifier models. So one of my goals for this talk was actually to incorporate a meme. So here's my meme. So, does it work in production? Right? You very typically have a data scientist will come along and create this amazing model and say it's great, it's better than what we have, offline metrics are incredible. Then you say, well, does it work in production? And of course it does, otherwise I wouldn't be showing it. So we launched this to production last year. So in an A/B test, we saw a good improvement in the operational metrics. So we have improved click-through rate, purchase-through rate, and revenue. And as you saw, we essentially try to maximize conversion, so try to maximize the purchase-through rate. And we were happy to see that the revenue was also increased when we launched the model. Because if we simply improved the purchase-through rate and recommended a bunch of cheap items, that might not actually generate additional revenue. So we're happy to see that the revenue was also came in with that. We could have maximized the click-through rate, but that's not as beneficial to the business as maximizing purchases. And so this was a site and category segmented model, and we launched it globally to full traffic last year. Okay, so what I talked about, I described some of the challenges that eBay had and the scale and the type of data that we have and how we address that to generate meaningful recommendations. So I talked about one approach that in detail that we used the machine learning ranking model for similar item recommendations and how we made a scalable architecture to address that problem. Overall, I just wanted to give you a taste of some of the work that we do at eBay, kind of what it looks like, what the engineering looks like, what the machine learning and deep learning challenges are, and how we actually address them in our office down the street. So thank you very much, and we're hiring. Come talk to us. We have a booth, and a few of us are here in the room. So thanks a lot. If there's any questions, happy to take them. Yes. Sure. Yeah, great question. So logistic is fast and it's easy. So that was our first choice. We've actually tried a few other models, and actually they didn't do better. They did it roughly the same. So it didn't actually, the classification performance, the offline metrics were slightly improved, but operationally it didn't actually make that much of a difference. Also, we played around with PMML format to actually transfer the models from offline to production. Found like there was no actually industry-wide standard to do that, and so we had some of our own. So that was interesting. Logistic regression is also very easy to implement at prediction time. Some of the other classifiers are not as easy. PMML, yeah. Yes. So you can. So there's some libraries. I mean, it's called JPML Evaluator. So we're a Java-based org, like we use the JVM very much. So that's a Java library, and that can actually evaluate your PMML exported file. So that's the one way. There, you can evaluate the performance in terms of speed, but for us it seemed to work. It depends on your engineering constraints, I think. We didn't see we didn't see an improvement in the GBM model actually. It wasn't deep, just like the tree-based models performed roughly similar. Yeah. The deep models we do it for the image similarity. It's sort of a sub-process of the whole algorithm. But for the ranking, we used the sort of traditional classifiers for the time being. Which kind of? So you mean for like a deep learning approach? So we haven't done a deep learning ranking yet. That could be potentially our next step, but that's I think haven't tried that yet. Yeah. All right. Thank you.